Southeastern Saskatchewan, early morning of February 26, 1979. Approximately 7 kilometers west of Carnduff. Today is a special day. We will see one of nature's most awesome spectacles, a total eclipse of the sun.
Right here?
Yeah, just move up a couple more feet. Go south.
A group from the Royal Astronomical Society of Canada, Saskatoon Centre, has traveled to this location to observe the eclipse. They are setting up their equipment, telescopes, cameras, and other equipment, hoping to record the event.
Things like that are help.
Where's that set?
Okay, next thing I gotta do is find that post. Get a focus on this thing and find that one here.
It is cold this morning, cold and clear. Hopes are high for a good view of the eclipse.
Oh, no, I think
Despite the cold, equipment must work smoothly, and film must not bind or break in the cameras.
get everything looking in the same general direction.
Yes. No,
Yeah, we got power here.
doesn't matter.
Now.
Yeah. Here's that.
Setting up the equipment started the night before. In order for the telescopes to track properly during the eclipse, they must be aligned by the stars the night before. And tonight this is somewhat difficult because of a high, thin overcast.
Okay, make sure they're tight.
But as the evening progresses, the stars become visible, and the alignment procedures continue.
You said it when at second contact.
Bites the sun.
Yeah.
Okay.
No, not as at second contact. When the minute the instant totality starts, you start that timer going.
Okay, at 2:35.
And the minute that thing goes off, it won't be heard by everybody. You start your siren going.
Okay, but do you know the time on WWV when exactly for television?
No, but that'll be called out.
Okay.
That,
Because I don't want to sit there and look and say.
no,
well,
no,
it's like, oh,
no. Jim will probably call out the setup on totality.
The alignment must be as precise as possible, so time won't be lost adjusting the telescopes during those few precious minutes of totality next day.
Clear it up a bit.
Okay, we're right, except I haven't allowed for the way the camera's yet, so I have to put those on.
Everybody's aligned? Everybody knows where they're gonna go? Are we all set?
I think so. I think we've got everything, haven't we?
After alignment procedures are complete, the telescopes are removed for the night, and the telescope mounts are left in position. In the morning, the day of the eclipse, telescopes and cameras will be remounted in anticipation of the event. For some, it will be a night of preparation and little sleep. The wait begins. Since ancient times, man has been fascinated by the heavens. The Egyptians called the sun Ra and saw its rising, passage, and setting each day as a symbol of birth, life, and death. The sun was worshipped, as was the moon. And on the practical side, they aligned their monumental buildings, the pyramids and temples, by a land survey system based on observation of the stars. Other ancient peoples, such as the Sumerians, Chaldeans, and Babylonians, built magnificent temple towers for the worship of the sun and the moon, and for observation of the heavens. Over the millennia, they came to be able to predict the occurrence of solar eclipses with some accuracy. Observations in China were largely for astrological purposes. And often it was an offense by royal decree to disseminate astronomical information to the populace. By 500 BC, the Greeks had various thoughts on the nature and structure of the universe. Dr. Len Greenberg, Department of Physics and Astronomy, University of Regina, explains.
And going back further, about 500 BC, it seems that Pythagoras was the one who first got the idea of a round Earth, and that was, quite a revolutionary idea. And in the years to come, they even had the idea that the Earth and the Earth went around the sun, the moon went around the Earth. So they were able to figure out even the cause of eclipses, and quite correctly too. What's more fascinating, though, is that they were able to predict eclipses. And this means that they must have had calendar systems dating back a couple of hundred years. They must have had records that people were able to go over. They went over these records and found that the eclipses occurred in cycles over about 18 years, and another cycle of about 54 years. So they really knew a lot more than we ordinarily would think.
In Europe, man's interest in the heavens goes back thousands of years, as evidenced by such structures as Stonehenge in England, a large megalithic sundial and calendar built about 2600 BC, and used for astronomical observations, as well as religious rites. Similar structures elsewhere in Europe are now being researched, and their astronomical significance is now being realized. The ancient Indians constructed medicine wheels. Some of these stone designs, such as this one in the Moose Mountain area of Saskatchewan, are in excess of 60 meters in diameter. While still being researched, some people believe these have astronomical significance. In Central America, structures such as this Mayan observatory were built expressly for observing the heavens, for both religious and practical purposes. And calendars were independently developed by various Mesoamerican cultures, such as the Aztecs in Mexico. Ancient astronomy produced the calendar we use today. An Egyptian invention provided a basis for land survey and navigation at sea. The ancients grouped the star patterns to represent mythological characters, and systematic observation with predictability of phenomena was largely a side benefit of the prime purpose of observation. The divination of future events by movements of the stars and planets, the beginning of the present-day pseudoscience of astrology. The moon, goddess of the night, and the sun, giver of light, were observed and venerated throughout the ancient world. The movements of the heavenly bodies were construed as omens for good or bad, and the solar eclipse was considered a portent of the success or failure of armies, kings, and often shaped national decisions. Before the invention of the telescope, controversy centered around the nature of the universe, whether it was geocentric, the whole universe revolved around the Earth, or whether it was heliocentric, the planets revolved around the sun, and the sun was a small part of the greater universe. The work of astronomers, such as Copernicus and Kepler, verified and made popular the sun-centered theory, and proved that the sun was indeed the center of the solar system. In the 16th century, with the invention of the telescope, astronomy changed from a largely mathematical science to an exploratory science. Galileo drew some of the first maps of the moon and may have been the first to observe sunspots. The telescope and its use coupled with other developments in the physical sciences in the 18th and 19th centuries, resulted in the emergence of modern astronomy. Dr. Ishrat Naqvi of the Department of Physics and Astronomy, University of Regina, describes these developments.
Galileo used the telescope for the first time for astronomical purposes in early 17th century, but it was not until the 18th and 19th century that the real developments in telescopes came about. At the same time, it was not until about the end of 18th century that astronomy really became separated from its astrological and religious restrictions. And then, at that time, the astronomy got divided into three distinct parts. The observational astronomy, which is looking at things that one finds in the sky. Physical astronomy, which is the description of those things that one sees in the sky, and making of a theory about the origin and structure of the universe, that is cosmology. And the third was gravitational astronomy, which in fact was the foundation of the modern physics, modern science, in which the interaction between the bodies, like sun and the planets, and sun and the comets, and the orbits of the planets and comets were described. And the observation of the eclipses was an activity which was engaged as a part of, in fact, all three, and particularly of the observational and gravitational astronomy. And even to this day, the observation of eclipses, solar eclipses and lunar eclipses, is a very fruitful and useful activity in astronomy. Now, if a solar eclipse is taking place at a time when the apparent size of the moon is equal to or larger than the size of the sun, then the eclipse that we see from the Earth will be the total solar eclipse, because the total of the sun will be covered. On the other hand, other times when the apparent size of the moon is a little smaller than the apparent size of the sun, then the eclipse that we will see will be annular eclipse, because only a part of the sun, or partial eclipse or annular eclipse, because the part of the sun will be, only part of the sun will be covered. And so this will be the reason for annular eclipses or total eclipses.
Today, equipment for observing the sun is advanced, and very often is a fixed observatory, which cannot be moved to the eclipse path, such as the McMath Solar Observatory at Kitt Peak, Arizona. Our map shows eclipses in Saskatchewan for more than a century, back to 1860. And while there are no large solar observatories in Saskatchewan, over the decades, clear skies have attracted both amateur and professional astronomers to observe eclipses here. Morning, eclipse day. The overnight wait is over. The weather looks good. Clear skies, cold, some light ground fog. Telescopes and cameras are being loaded onto the mounts set up the night before. Within an hour, most of the equipment is ready to record the eclipse. Final adjustments are being made. Soon the eclipse will begin. Expedition members will feed data to a central location during the eclipse. How the data will be recorded is explained.
The purpose of this equipment is twofold. On the audio tape recorder, we're recording a time signal on one channel, and on the other channel, we're recording all of the major photographs that we're taking. On the strip chart recorder, we have on one channel a precise time signal, and on the other channel, we were monitoring the ambient light level during totality. As a matter of fact, with this equipment, we should be able to precisely correlate the times of contact of the eclipse.
First contact. The moon begins to bite into the disk of the sun. The eclipse is underway. The moon moves across the face of the sun. The landscape begins to darken. The temperature drops somewhat. As the eclipse progresses, expedition members photograph the partial phases. Checks are made of falling temperature. Photometers measure the steadily decreasing light reaching the Earth from the sun. The sun is now almost totally eclipsed. An eerie twilight pervades the landscape. In moments, the eclipse will be total. Along the limb of the moon, the light from the sun appears broken in places. This is caused by sunlight being obstructed by and passing through the mountains and valleys of the moon. The phenomenon is known as Bailey's beads. In the last few moments before totality, we see a final bright flash of sunlight, the beautiful diamond ring effect. The solar corona, the sun's atmosphere, is now visible as a halo of light extending out into space. It actually extends hundreds of thousands of kilometers. We also see the solar prominences, bright flares extending some 30,000 kilometers from the surface of the sun. With totality, the overhead sky becomes quite dark. The temperature drops a number of degrees. All around the horizon, 360 degrees, the sky takes on a ruddy sunset effect. And in the dark sky above, the brightest stars and planets become visible, such as the planet Venus, shown here to the far right of the eclipsed sun. The exit diamond ring marks the end of totality as sunlight floods past the disk of the moon. Totality is now over, a bare 2 minutes and 45 seconds. Filters on telescopes and cameras, removed to record totality, are now quickly replaced to avoid damage to eyes and optical systems. With the end of totality, expedition members continue to photograph the partial phases. The increased light from the sun is measured. Temperature increase is noted. The sun now appears quite bright, and the limb of the moon is not easily visible. But with a filter, we continue to see the moon move from the face of the sun. Last contact. The eclipse is now over. From first contact to last contact has been approximately 2½ hours. Some of the participants of this expedition describe their experiments and the chances of success.
The purpose of this experiment was to observe and hopefully record shadow bands, which are very faint, very diffuse bands of shadow that move across the ground just before and just after the total part of an eclipse. As to whether we got any this time, we're not sure. We really won't know until we develop our film, but we're hopeful.
Our project was to get a motion picture of the eclipse in just about 4 minutes. So what we had was a 16mm cine camera and a 6-inch reflector to track the sun. And using the camera, we took one shot, one frame every 12 seconds during the partial phases, and during totality, we ran it for two minutes. So what we hope to get is a complete record of the eclipse in just about 4 or 5 minutes.
My project was just to take pictures of the eclipse with this, and with a neutral density filter on the top here to block the sun's rays. And we use clock drives in this to keep it on track, and just use our cameras to take the pictures.
My project was using the Astroscan to take a series of photographs through it upon first contact till the fourth contact, and of course it is a wide-angle lens, and we had the filter put on the front here. And I used a LabRack 35mm camera on it. And I photographed 125th of a second until totality, and then the thing froze up, I think, because it didn't work after that. So I went back to my movie camera.
This experiment basically consisted of 3 experiments. There's 2 telescopes, the Celestron 8 and the Celestron 5. Both fitted with filters on the front. These are neutral density 4 filters. There's a filter on the finder, and the side view would present this with 2 cameras. He's both taking pictures. Now, the format for the 8 is too large to get the corona, so that this was primarily centered around the prominences and the inner portion of the corona. The 5, because of the shorter focal length, would give me the full coronal effect, so that the pictures were taken on the 5 for the full corona. Additionally, we had a thermometer sitting down on the pedestal here, and at the approximately 15 minutes before totality, the temperature read -4 Celsius. The lowest it dropped during totality was -12, and just before we finished the experiment, it had come back up to -6 degrees Celsius.
Equipment is being disassembled and packed for the trip home. For some, it was their first eclipse. For others, one of many over the years. There are photographs to develop, data to analyze, old acquaintances remade, new friends found, the sharing of a memorable experience. February 26, 1979, a special day. Today we saw and experienced a total eclipse of the sun. The last total eclipse visible in North America this century. There will be others, but North American residents will not see one again till the year 2017.
It's 11:30 a.m. 107 degrees west, 53 degrees north, 12 p.m. or a.m. It's noon. And there she is, skipping by. Cool. Down proud if you're watching. Here. That's why you can't see it. It's noticeably darker out, but that's all.